With this video, I have two goals for you. One is the basics of how to use Excel to calculate mean, standard deviation, and standard error. You're going to need these numbers to actually analyze your data that you collected for Lab 4. Then I want to walk you through the t-test, how you actually do the t-test, how to interpret the value, and what does it mean, and then talk a little bit about why we do a statistical analysis, help you understand that. But first of all, I want to orient you to your spreadsheet. Hopefully your TA went over this, but just as a reminder, on this spreadsheet here, if you look down at the bottom here, we have these tabs down here. And table 1A are going to be the data for treatment 1. If you recall, these are the plants that had no competition. So you had a single green or a single yellow plant. Table 1B here will be data for treatment 2, and this is the intramorph competition. So you had green competing with green and yellow competing with yellow. And table 1C here is the intermorph competition. So you had a green competing with yellow or yellow competing with green. I'll talk about table 4 later. But let's go back to table 1A. So as a reminder, you were measuring fitness by using components of fitness, and these are ways to estimate reproductive success without actually counting offspring. So here's an example that used plant height, number of flowers, and number of leaves. And again, these are basically, for all intents and purposes, a proxy of reproductive success. And then you have the data each group enters. So standard morph here represents the green plant, YG represents the yellow-green plant, and if you recall, you're measuring these data on a green plant and a yellow-green plant for the different components of fitness for this lab. And here are the data that, at least for this example, this lab section that they collected. So we got all these numbers here, and we ask you to calculate a mean, a standard deviation, and a standard error. And the power of a spreadsheet is it allows you to do these calculations very quickly with no error. You could do these on your calculator. That's perfectly okay. It will take longer, and there's a higher probability you'll punch something into the calculator wrong. But I just want to show you real quickly how you can actually use spreadsheet here to calculate these values, and it'll save you a ton of time on the homework. So first, let's talk about the mean. So the mean, the way you want to calculate that is in Excel. In most spreadsheet programs, when you want to do a formula, you type in equals. That tells the program you're going to do a formula. And then to do a mean on Excel, you can type in average, or if you hit A, now quite often this will pop up. So I'm going to click on that. So we're going to calculate the average here. And then there's these parentheses here. And so the numbers I want to average have to be in the parentheses. What I'm going to do here is I'm going to highlight the values I want to calculate the average on. So all the data here that were collected by the students. And this is going to grab the data from cell B3, which is this one right here. So column B, row 3, and grab all the numbers all the way to M3, so column M up here, and the same row right here. Once I get that in there, I just hit return, and voila, I've calculated the average pretty quickly. And then what I can do is, I do want to calculate this average here, but I don't have to retype that formula. I can just grab this little blue box right here, and I can drag that down to all these cells here, and in effect it is copied the formula all the way down here, but the average in this box, for example, is grabbing the data from this row. The average in this box here is grabbing the data in this row. So you can click on the cell here, and you can go up here, you can see exactly where the data are coming from. So that makes it nice and easy to calculate the averages. These number signs here, pound signs, hashtags, however you want to call them, there's no data here, so that's why you have, basically it's an error. And so you can clean it up by deleting that or leave it, it doesn't really matter. But since there's no data to be calculated, there's no data here, that's why that comes up. For standard deviation, you can do a very similar operation, do equals. The command for standard deviation is stdev, stdev, if I can say it. And you want to only use this one. There's different types of stdev commands here. You don't want to use any of these. You just want to use this one here. I'm just going to click on this box right here. The parentheses show up again. I'm going to highlight the numbers, the data I want to include for my standard deviation. hit return, and voila, I've calculated that pretty quickly. And then similarly with the averages, I can just drag that down, and I've calculated the standard deviation for all the data here. Now for standard error, you're going to use these on the graphs that we ask you to do. And for standard error, there is no formula in Excel for you to do this, but it's a simple formula. And the standard error is your standard deviation divided by the square root of your sample size. And our sample size here is going to be 12, and that's just the number of groups you had. So you had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 data points here. So our sample size is 12. And so we're going to take our standard deviation and divide it by the square root of the sample size. This formula is in your lab manual. You can look it up. So to do that, okay, click on the cell here. Again, I hit equals for a formula. I'm going to click on the standard deviation cell, so it's going to grab those numbers. Then I can do this. The divide sign is this hash mark right here. And then the square root of my sample size, so 12 is my sample size. There's a number of ways you can do it. You can just take 12, figure out the square root. In this case, the square root is 3.464. You can just type that in a calculator if you want. And I've calculated the standard error very quickly, and I can drag that down just like I've done before with these others. You can also calculate the square root of your sample size by taking 12, raise it with a caret to the power of 0.5. If you recall, if you raise something to the power of 1/2, it's taking the square root. That'll do the same thing for you. Or there is a square root function here. It's SQRT. Then in parentheses, you put the number you want to square root. In this case, it's 12. I click on that. It gives me the same value, and I can just drag that down. Same numbers. Now there's some rounding here, but effectively they're the same numbers. And so there, I've calculated the mean, standard deviation, and standard error very quickly. You're going to want to do that for table 1B and table 1C. So now what do you do with that? So now you want to do a t-test. So I'm going to click on, drag this over here, click on, from your lab manual, the formula for the t-test, which is down here, and this is an important table right here. So your lab manual discusses the t-test and how to actually perform it, and in lab, hopefully you've gone over that. But let me go to this version right here. I've just pulled this out, put this in a Word document, just to make it a little bit easier for us to talk about. So here again is the formula for the t-test. Here's the critical t value, and this is critical for you to understand and be able to interpret the data correctly. We have a column here that's called degrees of freedom, and I'll explain what that means in a minute. But the first thing you want to do is you want to calculate your t value. You want to calculate that, go back here, initially for this set of data here. So you have these two averages for plant height. The green plant looks like it was 37.17, I'm assuming that's in centimeters, tall, and then the yellow green was 26.19. And so what we want to do is verify in a formal way that we're saying that these plants on average are bigger than these plants on average. Are the green plants bigger than the yellow green plants on average? We want to determine this with a formal statistical analysis, and that's what the t-test is going to help us do. So if I go back to this table right here, what I want to do is, let me scroll down here so I can have these numbers, you can look at them. We're going to calculate the t value here, and we're going to plug in the numbers that we calculated over here into these variables right here. So basically what we're going to be doing is taking the average plant height for the green plant and subtract from that the average plant height of the yellow-green plant. We could do it the other way, it doesn't really matter. But we're going to subtract the averages from each other. And then we're going to take the standard deviations we calculated over here. We're going to take the standard deviation and square it, divide that by our sample size, and add to that the standard deviation of the yellow-green plant divided by the sample size, and take the square root of that. And so I did that down here where I plugged in the values here. So we have 37.17 comes from this value right here. That's the average plant height for the green plant. 26.19 comes from this value right here. That's the average height for the yellow-green plant. I'm subtracting these from each other. And then I plugged in the standard deviation values here. So 4.305, 6.949. We square those, and then you divide those by 12. And when you do that, you get a value of 4.671. So that's our t-value. So what does that mean? So this is now where the table is important. So if I scroll back up here, we have a column here that says degrees of freedom. We have a column that says 90% confidence limit, one at 95% confidence limit, one at 99% confidence limit. So what we're trying to decide is how confident are we that this number is truly bigger than that number, or that on average the green plants are bigger than the yellow-green plants, or bringing it back to the story that on average the green plants have greater reproductive success than the yellow-green plants. So to do that, first we need to know what our degrees of freedom are. So our degrees of freedom is basically our sample size minus 1. So we had 12 data points for the green plant, and then we had 12 data points for the yellow-green plant. And so our degrees of freedom is going to be 12 minus 1 for the green plant plus 12 minus 1 for the yellow-green plant. You add those together, you get a value of 22. So for the degrees of freedom we're going to use is going to be 22. So 12 minus 1 plus 12 minus 1, or 11 plus 11. So we're going to only focus on this row right here. These degrees of freedom, if you had a smaller sample size, so if we had only 10 data points, the degrees of freedom would be 10 minus 1 plus 10 minus 1, or 9 plus 9, which would be 18. And so this table allows for other differences in sample size. Next thing we want to do, we want to take our value here. You want to compare 4.671 to these numbers here in the table. And so in order for us to say that this number is truly different from this number at a certain confidence level, the number we calculate, this one here, has to be larger than the values in here. So we have a pretty large number here. So 4.671. That's bigger than this number right here, 1.717. So we know we could be 90% confident that the green plants are bigger than the yellow-green plants. But we want a higher confidence level. We want to be much more confident than that. We want to take the highest confidence level that we can. So we go over here to the 95% limit. We have a value 2.074. Our calculated value 4.671 is bigger than that. So we know we could be 95% confident. But can we be more confident? And we can. And so at the 99% confidence level, we have 2.819. And so 4.671 is bigger than that. So we can be 99% confident that this value is bigger than that value. But what if our number is smaller than, say, 1.717? Say we calculated a value of, 1.5 at 22 degrees of freedom. We go to our table here, we see 1.5 is smaller than this number here. And because we have a value that's smaller than this, we can't say that this value would be bigger than that value, or that there was a difference in averages. We would fail to reject the null, or the idea that there is no differences between those. If we calculate, say, a value of 2 or 1.9, for example, we could say we're 90% confident 1.9 is bigger than this, but it's not bigger than this number here. So we could say we're 90% confident that the averages are different, but we can't say we're 95% confident. So we have a relatively low confidence limit. We always want to go for the highest that we can, and in science, usually 95% is the standard. But for the purposes of this lab, if you're 90% confident that works, that's okay. But keep in mind, usually the standard is about 95%. What you're looking for is a value that's higher than the one in this table here. And so that's what you're going to be calculating. And you're going to do this for all the data you're collecting. So you're going to be doing it for this set of data, this set of data, this set of data. Then on all the sheets here, you can do the same thing for table 1b. Calculate the averages and decide are they truly different, and the same thing for table 1c here. Going back and we look at some of these averages, this one's probably not different than that. And we look at it, they're pretty close, but we want to do a formal statistical test to verify that. And so that's what the t-test is all about. Why are we doing a t-test? So again, if you look at the numbers here to get 37.17, these are the numbers that you use to calculate that value. But if you notice, there's variation in the data. We have a range from a low of 31.8 all the way to a high of 48.5. Similarly, for this value here, 26.19, our data are ranging from a low of looks like 19 or 16 actually to a high of 36. So we have some variability in the data, and the standard deviation describes that to a certain extent. But what we're trying to figure out is this distribution truly different from this? So this is a distribution of the data, and we can calculate an average, just like your grades, right? There's a distribution of grades, and there's an average value for grades. And again, we're trying to decide, is this distribution truly different from this, given there's some variability in the data here? And so the t-test, if we go back to the formula of the t-test, takes that into account. So it takes into account the averages, takes into account that variation, but also takes into account your sample size here. That's why you're dividing by 12 here. And if you go to our table, again, the degrees of freedom is related to your sample size. So we had the end here, we had 12 groups or 12 data points for each plant, the green plant, the yellow-green plant. That gave us degrees of freedom of 22. But if we had a smaller sample size or smaller data set, we'd be in this range up here. And we would use these numbers here. And so again, we're taking into account our sample size. So the larger the sample size, the more confident the average we're actually calculating is truly representative. Whereas the smaller the sample size, the less confident we are on that. It's just like basically, think about Hardy-Weinberg. It's small population, genetic drift. It's a sample size thing. But if you look at the values, the confidence limit values, so if you look at, say, a sample size, degrees of freedom of 6, the numbers you're looking for are actually quite a bit higher than what you're looking for, say, of a degrees of freedom of 22. With a smaller sample size, you actually need more, a higher value of the critical t-value to say that one average is truly different from the other. Whereas with a larger sample size, that value is actually much smaller. So again, this is really related to your sample size, and the number you get is dependent upon the samples. So going back to our spreadsheet, so what are you going to do with that? So we can calculate a t-test for all of these data points, deciding whether this is truly different from that, is that different from that, is that different from that. Again, remembering this goes back to why are we doing this? These are proxies of reproductive success. Is there evidence of a difference in reproductive success between this plant and this plant, given there's no competition? When we use plant height, is this saying true or not, or is it not true if we use number of flowers as our proxy of reproductive success? And what can we discover? We use number of leaves as our proxy of reproductive success. Then you can do the same thing for competition, for intramorph, then intermorph. Then table 4 here, this is in your lab manual too. This is basically a summary of your data. So what you want to do here is just write your component of fitness. So plant height, number of flowers, what was it, number of leaves, I think. So you could actually type that in. Then our null hypothesis, you remember from lab 3, our null was a statement of no change, no effect. And we could write that formally mathematically, or we would say that there is no difference between plant height in the green plant versus the yellow-green plant. And we just write that with an equal sign here. So we could write that as, was it 37.17? 37.17 equals, go back here, 26.19, 26.19, oops, it disappeared. 37.17 equals 26.19. Should I get those numbers right? Yeah. And formally, we're just saying that there's no difference between these from a statistical perspective. And then what we're trying to do here with our alternate hypothesis is define what we mean by difference, that this number is different from that one. So you're going to write 37.17 does not equal 26.19. You're going to plug in your t-value here, whatever that is for your data, and then whether or not you reject the null. And you reject the null if your t-value is larger than any of those values in the table. And so that's what you can do on this sheet here. Then you can refer to this sheet when you answer some of the lab homework questions. Again, using components of fitness as our proxy of reproductive success, and we're deciding, again, for example, plant height, using plant height as our proxy of reproductive success, can we say there's a difference in reproductive success when there's no competition? At least for this component, we can say yes. We did our t-test. We can be 99% confident that that 37 is different than 26. We're basically the green plant is having more babies than the yellow-green plant. Then you would do the same thing for each component of fitness for each type of competition. So that's a quick summary of the t-tests. I encourage you to use a spreadsheet to calculate these values. It makes it a lot easier for you to do. For the t-test itself, I just suggest you do it by hand. You can use Excel and other spreadsheets to calculate a t-test. Sometimes it's hard to get the data right in there. You need to know what type of t-test you're doing. There's a YouTube video on everything. You probably could Google it or YouTube it. But it can be easier just to do it by hand too. If you have questions, come to office hours, talk with your TAs, and they can help you work through this as well. I hope this was helpful.